The purpose of our lecture today is to look at further considerations about state space representations of dynamical systems. For that purpose, I would like to describe a couple of dynamical systems examples and show you two things. First, the relationship there is between transfer functions and state space representations from the viewpoint of their mutual convenience. Second, I would like to show you the methods that exist for the purpose of representing transfer functions into state space systems. So, the first thing is state space representations and the what I would call use of redundant states. Which is also called non-minimality. The concept is fairly simple. Among all possible states, which we will call X, some might be too big. They are redundant. Some might be too small, and we have covered this concept already. For example, let's look at the following system. X dot, written in state space form, is equal to A times X plus B times U, where A is equal to 1, 0, 0. The second entry satisfies 0, 1, 0. And the third entry satisfies 1, 0, 0, 0, 1. Okay? In such a way that this is X dot is equal to X plus 1, 1, 1 times U. And we write that the output Y is equal to 1, 1, 1 times X. And we have the initial condition X of 0 equals 1, or let's say 2, 2, and 2. What is this system? Well, it is a diagonal system. if you think about it, it is the following. We have U that splits into 3 channels. The first channel, the second channel, and the third channel. And that feeds into 3 identical systems. S, S, and then S, which each satisfy x dot equals x plus u. And then those 3 systems provide an output, and those 3 outputs are summed up in such a way that you obtain y, and y is equal to x plus x plus x. So these 3 systems, which start at exactly the same initial condition, are totally redundant and could be simplified to the following. U feeds into the following system, S, and spits out y, which is now y is equal to 3 times x, if inside the system you only have x dot equals x plus u. Moreover, the initial condition is just x of 0 is equal to 2. Therefore, the following system, x dot equals x plus u, y is equal to 3x, and x of 0 is equal to 2, gives exactly the same answer as that system. Here the state has dimension 1, there the state has dimension 3. As such, you can imagine that indeed there are redundant states here that don't appear there. And the system here can be simplified into that system there. In which case, what we have is that this system is not minimal in the sense that it cannot be simplified. It can be simplified. Now, intuitively, we see that this system is minimal because it is very hard to simplify this system beyond a scalar differential equation, or to be more precise, a scalar first order differential equation. This is something useful to keep in mind as you go through derivations, because it is clear that manipulating this is simpler than manipulating that. Sometimes the opportunities for simplification are not as obvious as in this particular case. And we will not cover that topic to a much greater extent, but you should be aware of that distinct possibility. Therefore, I encourage you to think more about this. Let me now jump to another concern. If I erase all this, what I want to talk about, and that is a related topic, is the very possibility of having several state space representations for the same system. Let me show you an example that we have already considered in the past. It is particularly convenient because it is a system where you have already seen in your dynamics course. We just have two masses connected by a spring of stiffness K, of masses M, and which are pushed by a force F. The two masses M and the stiffness are equal to 1. And the coordinates of these systems are the choice of two things. First, what we call regular coordinates, where we call x1 the position of the first mass and x2 the position of the second mass. So that's a first way to describe this system. x1, x2, okay. Now a second coordinate system can be taken as xg, the position of the center of mass, and x sub r, the algebraic distance between the two masses. So let me repeat, distance, the sign distance between the two masses. Let's look at the equations of motion in both coordinate systems. Okay? In the first coordinate system, I have d dt of, or to be more precise, d squared dt squared of x1 is equal to the force F plus the restoring force K times x2 minus x1. Since all values are equal to 1, I will just write plus x2 minus x1. And likewise, d squared dt squared of x2 is equal to x1 minus x2. On the other hand, in the coordinates of the center of gravity and the distance between the two masses, here's what we get. As you probably remember, we can write that d squared dt squared of xg is equal to f and f alone. This equation should be familiar to you because it is an equation that you have seen in dynamics. Now, the equations in XR, the dynamics of XR, can be obtained by realizing that these two equations can be written as d squared dt squared of x1 is equal to f plus xr, and d squared dt squared of x2 is equal to minus xr, since xr is equal to x2 minus x1, the algebraic distance. Let me go back to this equation for a second. When considering the dynamics of xg, we need to weight xg by the mass of the entire system. If m equals 1 and we have two of these masses, we need to put a factor 2 here. Going back to these equations, one way of making xr appear on the left-hand side is to take this equation minus that equation. We will see x2 minus x1 appear. So we can write that d squared dt squared of x2 minus x1, which is d squared dt squared of xr, is also equal to the difference between this term and that term, that is minus f minus 2xr. So we have this equation of motion on the one hand when we look at this coordinate system, and we have that equation on the other hand as far as using the more natural or canonical coordinate system is concerned. How do we go from there? So what we're going to do is we're going to derive the state space equation for these two systems. For that purpose, we will erase a little bit of the available board, and we will write that as far as the first set of equations is concerned, we can rewrite that in the ABC form by introducing the state x1, x1 dot, x2, x2 dot, okay, and we call that x, and we write that d dt of x is equal to an A matrix and a B matrix. The A matrix reads as -1, 0, 1, 0. Oh, my mistake. The first row, because it's d dt of x1, which is just x1 dot, the row will look like 0, 1, 0, 0. The second row, which is d dt of x1 dot, which is x1 double dot, will be, as far as the states are concerned, -1, 0, 1, 0. The second state reads about similarly, d dt of x2 is equal to x2 dot, and d dt of x2 dot is equal to x1 minus x2, 1, 0, minus 1, 0. Now for the fourth terms, it will become 0, 1, 0, 0 times f. Now we'll talk about the outputs later, but let's now move to these dynamics instead. We can define another state to be, and let me move this picture a little bit. The state would be, we're gonna call it Xi is equal to xg dot xr dot. And we can write the equivalent expression, or another expression to be more precise, which is d dt of Xi. For those of you who are not familiar with that letter, it is a Greek letter which means almost like x, is equal to a certain matrix A again, and a certain matrix B. The A matrix will be as follows: d dt of xg is just xg dot, so it is 0, 1, 0, 0. d dt of xg dot, which is f over 2, doesn't have any participation in the A matrix, so we will skip it for now. On the other hand, d dt of, so we will put 0 as far as the state influence is concerned. On the other hand, as far as xr is concerned, d dt of xr is equal to xr dot, so this gives us a 0, 0, 0, 1 entry in the A matrix. And d dt of xr dot is equal to minus 2xr, so it will be 0, 0, minus 2, 0. And now we add the F, or the B matrix, and that is equal to, so this is Xi, and we write plus, and now we put the F element into it, and for this one it will enter as 1/2, so it would be 0, 0, 1/2, sorry. And there it would be minus 1, so it becomes 0 and minus 1 times f. So this equation is the same as that equation, it is just written in standard form. What you can see is a variety of things already. One of them is that the matrix here is hard to understand from the viewpoint of what it does. Okay? This matrix here has what's called some diagonal structure, which means that if I partition the matrix into these two blocks, you have a block here that appears, a block there that appears, and these two blocks are independent. Now, let's try and simplify things a little bit. In the picture, let's erase part of that picture by eliminating all these. Now that we have access to the state space form, which is what we wanted, and the only thing we wanted from the basic equations of motion. Let us talk about the output y. We're going to take the same output for both systems. Okay, so we're going to call y here must be equal to, I'm going to say it is xg. If y is equal to xg, we can write that it is equal to x1 plus x2 over 2 on the one hand. And therefore, in that notation, y is equal to 1, 0, 1, 0 times x. Here, y is simpler because y is equal to xg. Therefore, y is equal to 1, 0, 0, 0 times c. Several observations are in order. One of them is that since this derivation is legal and that derivation is legal, the two systems should be absolutely equivalent to each other. However, they don't look the same. Therefore, we need to understand how we can go from one system to the other. Second, there is a lot more structure in this representation than in that representation. In this representation, we don't have much immediate understanding of the system. And in particular, it is not obvious that the system can be greatly simplified. Whereas here, the system can be greatly simplified. Indeed, we can draw the system as follows. We have a force F at the input. The force F splits and feeds into two subsystems. The first subsystem is going to be, let me correct this. The first subsystem is going to be summarized by a 2x2 A matrix here. So I'm going to write it just in the form of the AB matrix. Okay? The local AB matrix is going to be 0, 1, 0, 0. And then the B matrix is going to be 0, 1 half. Okay? On the other hand, the system feeds into that second subsystem whose A matrix is different, but it is 0, 1, minus 2, 0 on the one hand, and on the other hand, the B matrix would be 0, minus 1. If you look at Y, it consists of taking that output and observing Y. You see the two zeros here mean that this part of the system, which is that part of the system, is actually connected nowhere. Y reads it independently from here. Y doesn't read this thing. In other terms, this part of the system may exist, it may be moving, but as far as reading Y is concerned, doesn't count for anything. Which means that this system can be, in fact, simplified to d, and we're going to call it psi dt is equal to 0, 1, 0, 0 times psi plus 0, 1/2 times f, y being equal to, and I run out of space here, unless I move this down, I can write that y is equal to 1, 0 times psi, where psi is 1, 0 times the state, or the reduced state, xg. Sorry, let me correct this. Psi is a state, and it is the state made of xg and xg dot. Therefore, we know this system is greatly redundant. There are too many states. But in this representation, it is not at all obvious to see what states need to be eliminated. Whereas in this representation, it is obvious what states need to be eliminated. So this is a first observation. The second one is that we need to study, because these two systems are equivalent, how we can go from x to xi and from xi to x. There must be a simple transformation that takes this system and transforms it into that system. So, we will now establish that this system and that system are equivalent to each other. For that, I will clear out this system and talk more in the language of linear algebra. This may be a little painful to you, but I hope very much that you will be able to follow. I said that xg is equal to x1 plus x2 over 2. Likewise, xr is equal to x2 minus x1. I can therefore say that xg dot is equal to x1 dot plus x2 dot divided by 2, and that xr dot is equal to x2 dot minus x1 dot. If I write this in state space form by respecting the order in which xg dot appear, I can write that equivalently the vector xg dot, xr dot can be written as a matrix, a certain matrix, times x1, x2, x1 dot, x2 dot. To be more precise, I am going to populate the entries of this matrix, and I'm going to recall that the vector I care about at the outset is x1, x1 dot, x2, x2 dot. Therefore, at the input, at the output, I will have xi, and at the input, I have x. The matrix will be populated as follows. xg is equal to x1 plus x2 over 2. So it will be 1/2, 0, 1/2, 0. xg dot likewise will be 0, 1/2, 0, 1/2. xr is equal to x2 minus x1, so it will be -1, 0, 1, 0, minus x1 plus x2. And xr dot likewise will be 0, -1, 0, 1. Okay, so I will use this as a way to transform this system into that system. First, I realized I forgot to put an x here. So let me add it here. I have xg dot, which is xi as a function of x1, x2, x1, x1 dot, x2, x2 dot. So what I will do is replace xi by its value in this differential equation. And what do we obtain? In order to simplify this equation, okay, this matrix, I will call it P. Now in the book, you may see it as P inverse instead. I'll let you figure that out. It doesn't really matter. If I call this matrix, I will call it A, that matrix B, and that matrix C, here is what I can do. I can replace xi by its value here. And what I obtain is the following. I will add a new, no, I cannot put it new. I need to make room somehow. I will clear out this area because most of it we remember. I will remember, so first I clear out this area. I will remember that the original y here was equal to yg, so it was 1/2 0 1/2 0. It's x1 plus x2 over 2, so times x. And here I got that y was equal to 1 0 0 0 times c. Let me plug in here the expression for c. I obtain d dt of p times c, right? This is p times x, sorry. P times x is equal to a times c, which is p times x, plus b times f. Again, this is c and this is c. And we have that y is equal to, if we call this matrix c, c times c, which is c times p times x. Okay, so another way of writing this is by placing the p on the other side. P can go out of the derivative and then we can invert it. I obtain d dt of x is equal to p inverse a p x plus p inverse b times f. And y equals cp times x. Now this x and that x are the same. Therefore, we should be able to match this matrix to that matrix, this matrix to that matrix, and this matrix to that matrix. Let's see if this is correct. For the purpose of doing that, I need p but also p inverse. P inverse is the process by which you go from these guys back to these guys. I'm going to clear out this part of my board and write that out of common sense, x is equal to, so x1 is equal to xg minus 1/2 of xr. x2 is equal to xg plus 1/2 of xr, since xr is the algebraic distance between x1 and x2. Okay, x2 is 1/2 part of XR away from XG to the right, thus the plus, and this one is is XG minus 1/2 of the distance to the left, thus the minus sign. And X1 dot is equal to XG dot minus 1/2 of XR, and X2 dot is equal to XG dot plus 1/2 of XR. So what I need now to do is write this in matrix form. Since this is a rather busy transparency, I will first move this guy up and then make some room there. Okay? Very good. I am going to write in matrix form these relations by writing that x1 dot, x2 dot are function of xg and xr. This vector, which is also x, must be equal through this relation to a certain matrix times xg dot, xr dot. And we get x1 is equal to 1 times xg plus 0 times xg dot minus 1/2 of xr plus 0 times xr dot. x1 dot is equal to 1 times xg dot plus 0 times xr minus 1/2 times xr dot. x2 is equal to 1 times xg plus 1/2 times xr and x2 dot is equal to the corresponding quantity which is xg dot plus 1/2 of xr dot. That, of course, is C. If this is the matrix that transforms you from X to C, that matrix is the one that transforms from C to X. That matrix must be P inverse. I am talking about that matrix here. So, let me erase this thing. And let me see if I have the proper result, which is that by correspondence, CP must be equal to that value, P inverse B must be equal to that value, and P inverse AP must be equal to this. That is, this gets transformed to that, this gets transformed to that, and this gets transformed to that. Let me start with the easy one, which is we're going to compute C times P. C times P is equal to this matrix times that matrix. It is very easy to see that this will be equal to, by computing this product, I'll let you do it, and I will obtain 1/2, 0, 1/2, my mistake, 0. Now, this is exactly equal to that matrix. Therefore, I indeed have that this matrix gets transformed to that matrix. Okay? Now, let's look at this matrix here. P inverse times B. B is here, P inverse is there. P inverse times B will be equal to a column vector, which we obtain by multiplying the rows of P inverse by the columns of B. The first entry will be this row times that column, and we get 0. The second entry will be this row times the same column. Therefore, it will be 1/2 plus 1/2. And this will give us 1. The third row is this times that, and we obtain 0. And the last entry will be this times that. So this row times that column. And when you compute the product of this row and that column, you get 0. Now let's compare this with that, and we see they are identical. Therefore, we indeed have that the transformed of B from C coordinate to X coordinates is exactly what it should be. Last, let us compute the more difficult, which is P inverse times A times P. It is difficult because we need to compute the product of a matrix with two other matrices. For that, I will make some free space by erasing this. Now we know that they are the proper match. And probably by erasing everything having to do with non-A related material. So we're going to clear Y, and we're going to keep A. So the first thing we're going to do is compute A times P. A times P is that matrix. We're going to compute first P inverse times A. Okay, so that will take care of this element. Why is it better? Well, because P inverse times A is graphically easier to compute. It's going to be this row times this column, etc., etc. So we compute P inverse times A first. And we get that this is equal to the following matrix. First top left entry, this times that, plus 0 times this, plus minus 1/2 times that, etc., etc. We get a 0. Now, we can compute again this to get the second entry, which is this one. We take this guy and multiply by this guy, and then we multiply these 3 zeros by these 3 numbers, and therefore we obtain 1. For the third entry, we keep doing the same thing, and we obtain 0. And for the fourth entry, again, we obtain, let's see, 1 times 0 plus 0 times 0 minus 1/2 times 1. We obtain minus 1/2. Okay? So this is P inverse times A. Now, the second row goes about the same. 0 times this. Okay, so the second row is going to be 0. In fact, the third row is going to be 0, and the fourth row is going to be 0, since we multiply this matrix by that matrix. And then, the second row, second entry, is going to be 0 as well. The third row, no, the second row, third entry is going to be minus 1/2 times minus 2, which is 1. The last column, the last component of the second row will be this times that, plus that times that, plus that times this, plus this times this, which is 0. Third row, we're going to compute the second column, 1 times 1, and then a bunch of zeros. 1. Then the second entry will be 1 times 0. Okay, it's going to be 0. And the fourth entry is going to be 1/2, multiplying this term by that term. Finally, the last row, second column, will be 0. Last row, third column, will be minus 2 times 1/2, which is minus 1/2. And then we just get a 0 for the last entry. So that's P inverse times A. Now we need to take, in order to get P inverse times A times P, we need to multiply this guy by this guy. Okay? So let me simplify things, and I'm going to make an entry here. P inverse times A times P is equal to, well, we're going to get a 4 by 4 matrix whose first entry is going to be 0 times 1/2 plus 1 times 0 plus 0 times minus 1 plus minus 1/2 times 0. Therefore, 0. The second entry is going to be 0 times 0 plus 1 times 1/2, etc., etc. Okay, so let me do it again. 1/2, sorry, so the second entry is going to be 1/2, 0 times 0 plus 1 times 1/2 plus 0 times 0 plus minus 1/2 times minus 1. It will therefore be 1. The third entry will be 0 times 1/2 plus 1 times 0 plus 0 times 1 minus 1/2 times 0. Therefore, 0. And the last element will be 0 times 0 plus 1 times 1/2, and you can see minus 1/2 times 1, 0. Second row, 0 times 1/2 plus 0 times 0 plus 1 times minus 1 plus 0 times 0 is equal to minus 1. The second entry will be 0 times 0 plus 0 times 1/2 plus 1 times 0 plus 0 times 0. Third entry, 0 times 1/2 plus 0 times 0 plus 1 times 1 plus 0 times 0. 1. Last entry, 0 times 0 plus 0 times 1/2 plus 1 times 0 plus 0 times 1, 0. Third line, 0 times 1/2 plus 1 times 0 plus 0 times minus 1 plus 1/2 times 0 gives 0. Second entry, third row, 0 times 0 plus 1 times 1/2 plus 0 times 0 minus 1 times 1/2, 0. Third entry, third row, 0 times 1/2 plus 0 times 1/2 plus 1 times 0 plus 0 times 1 plus 1/2 times 0, 0. Fourth entry, third row, 0 times 0 plus 1 times 1/2 plus 0 times 0 plus 1/2 times 1, 1. Last row, 0 times 1/2 plus 0 times 0 minus 1/2. Hold on a second. Let me repeat. Okay? So we do 0. Hold on a second. So hold on a second. Okay. So 0 times 1/2 plus 0 times 1/2 plus 1/2 times 1 plus 0 times 0 equals 1/2. There's a mistake. There's a mistake because this 1/2 should be a minus 1. So let me recompute P inverse times A. The last row, third column, 0 times 0, 0 times 0 plus 1 times 0 plus 0 times 0 minus 2 times 1/2. I knew it. There was a mistake there. This guy ought to be minus 1. Okay, so let's restart our computation as far as P inverse AP are concerned. So the first entry is going to be 0 times 1/2 plus 0 times 0 plus minus 1 times minus 1 plus 0 times 0 is equal to 1. Now, second column, last row, 0 times 0 plus 0 times 1/2 plus minus 1 times 0 plus 0 times minus 1, 0. Third column, 0 times 1/2 plus 0 times 0 minus 1 times 1 plus 0 times 0 minus 1. And last column, fourth row, 0 times 0 plus 0 times 1/2 minus 1 times 0 plus 0 times 1, 0. This matrix is to be compared with that matrix. And what we see is that once the numerical errors have been fixed, these two matrices are equal. Therefore, what we have is the proper transformation here. When we go from one coordinate system to another, this is the way to transform the matrices in order to get the equivalent dynamical system. Okay? The equivalent state space representation. And therefore, we have formulas to go from one state space representation to another state space representation. This is extremely convenient because some state space representations are better than others. Thank you.